We have Solomon, can you hear me? You can hear? Okay, fine. Okay. All right. Due to large number of audience, I have changed my topic and I'm going to discuss highlight contribution in fuzzy logic of bibliometric analysis. Bibliometric is basically a kind of literature review, but it has three components. The first is what we call statistical, second is graphical, and third one is metric. So collectively, we call it bibliometric analysis. So in this analysis, we discuss any three aspects depending upon the requirements of the or the objectives of the person or the paper, anything. So in this paper, I am going to discuss Thailand contribution in fuzzy logic, and I will demonstrate how we can extract data from database, how we can plot that data, and how we can interpret that data. But just for some example. So basically, we know that fuzzy set theory is a very famous topic in applied and computational fields because it allows us to deal with the uncertainty. And uncertainty is a part of our daily life. Second, there is a large number of growth has been seen globally due to its relevance in interdisciplinary applications. This fuzzy logic now can be applied from medical to any pure sciences as well. So, uh, sorry, here I have to change Thailand. So objective of this study was to analyze the growth and development. Sorry, I have used any other slide. Here, Turkey. Oh, I'm sorry. Let me change my slides. Okay, let me quickly, swiftly change this to. क्या to perform this. So again, this way. So I'm sorry for this inconvenience. Let me show why, what was the motivation behind this study. So when we explore Scopus database with a keyword first star, here we use star. Is steric means fuzzy set, fuzzy logic, fuzzy sets and systems, or anything that comes next to fuzzy. So we put star in databases. In both the databases, if we are using Web of Science, then or if we are using Scopus, So we use first star. So here you can see that as I put first star, so it means fuzzy logic, fuzzy sets, fuzzy controls, and whatever the keywords are. So we search here, and what we get is, oh, sorry, I have to share full screen. Yes, I have to share full screen. Okay, let's go back. So to start, to search in this database, we use first star. So steric means now whatever next is fuzzy logic, sets, controls, or systems. So we are going to search all this data collectively. Here we can see that 77,512 documents are found till date. So we scroll down, we go to the countries and territories, and here we will find Thailand. So Thailand is currently with 3,031 documents to date. So this motivates us to study this topic or to find out the bibliometric analysis of this fuzzy logic in Thailand. Now we have 3,031 documents. So we go to the tab export, we click here and then we go to the CSV file. Here we have to select the documents and it gives us 3031. We can download 10,000 documents in Scopus database in one go. And we have to select all the options because we have to plot this data. So we select all the tabs from here and then we click export. Uh, it will take some moments. So this bibliometric analysis is very important. Or now we can add first chapter of our thesis work as a literature review where we have to explore lot of research papers or topics, and then we go to our research problem and then we investigate that. So simply using these databases, we can find a research gap. So for example, my thesis topic was linguistic hypersoft set. So when I was working on this term, we can use operators in databases here. So I have selected one keyword is a linguistic, and I have used operator and I have second is hypersoft set. So when we search this from the databases, we found that we have only 5 documents. And here you can see that these all the documents are published by me and my supervisor. So this was the motivation at that moment when we started working on this topic. At that time, there was no single document that was published with linguistic hypersoft set. So every decision making is based on the term linguistic because linguistic is linked with the knowledge or the language. And without understanding of language or knowledge, we cannot move towards the decision making. So that was the motivation behind my thesis work. So similarly, every student or a scholar can explore his research gap simply by using these operators in databases. This is just one database. Similarly, we can do this analysis in Web of Science database and we can search our relevant keywords. So at that moment, there was no document, so I decided, and then I have explored all the other aspects of literature review, and then I worked on this topic. And right now we have more than 10 documents that has been published. Actually, some journals are not indexed in Scopus, so we can find them in Web of Science. So now we have our document is ready that has been downloaded. So we will download a software Wasware for analysis, and we go to the second tab where we have used a create a map based on bibliometric data. Here we select a tab Scopus. We upload our data file. I have already uploaded this file. Now we have a Wasware based. This is basically a graphical analysis of literature review that we have a data right now. And that data is fuzzy contribution of Thailand. So I have downloaded from Scopus database. Now I'm going to visualize with the help of Wasware. Here we have many options. We can find out the co-authorships. We can find co-occurrences, citations, bibliographic coupling, and co-citation. But moving on, first we have to select a more important aspect here, and that is full counting or a fractional counting of authorships. Full counting or fractional counting of authorship. If we select full counting, so it will give one value to one author at a same time when we have more than one author in a single document. For example, in my paper, we are 3 authors. So now when we use Wasware for graphing, and if we select full counting, then it will give one value to me, and for my rest of the authors, there is no value. So even though they are a part of my research work. So we have to select here fractional counting, and then we can move forward. So in this fractional counting, if we are 3 authors, then it will equally divide value 0.33 to all the 3 authors, and then we can move towards the graphical analysis. So we have a lot of options here. Here, bibliographic coupling has different meanings, co-occurrence meanings are different. So I will move straight forward to that here. So basically, first is metric analysis, and this metric analysis, yes, okay. So metric analysis focuses on the number of publications. Co-citation analysis, in metric analysis, number of citation means total citations, I-10 index, H index, like this, we call them metric analysis. Next is co-citation analysis. So it investigates how often 2 publications are cited together in subsequent work. In one single document, how often 2 documents are cited together. In fuzzy set theory, for example, I am working, and a base of fuzzy set theory was the paper published by Lotfezadeh in 1965. And then we move forward towards the hypersoft set theory. In hypersoft set theory, paper was published in 2018 by Florent and Samranche. So how often those 2 papers are cited together can be studied with the help of co-citation analysis. And what will be the benefit of this analysis? This is very important. So used to identify research clusters and intellectual structures in a field. If 2 different documents are cited together, it means that they have some intellectual connections between them. So when we do co-citation analysis, it helps us to find those intellectual linkages. Next is bibliographic coupling. So it analyzes the number of references shared by 2 documents. 2 different documents are citing one single document. Before this, in co-citation, 2 different documents are cited in a single document. Now in 2 different documents, a single document is cited. So this is known as bibliographic coupling, and it indicates the connection between the two topics. And last is co-occurrences. So co-occurrence is used to analyze potential relationships between bibliographic items that appear in the same paper. So in single paper, what are the key themes, are the key topics, are the clusters? So this is used for these purposes. So in bibliometric analysis, basically we have four parts. First is a metric analysis, that is simply can be extracted from the databases, either from the Scopus or the Web of Science. Next, is there a need for co-citation analysis, bibliographic analysis? But when you are doing a literature review, or you want to find out a case study, or you want to see nowadays fuzzy logic is aligned toward what direction. So we simply go towards the co-occurrences. We do a bibliometric analysis with the help of was-where. It will give us some keywords, and then we can analyze that. So fuzzy is now aligned towards more machine learning, deep learning, neural network, or what are the keywords. So basically, this slide is most important in bibliometric analysis because it helps us to uh, uh, find out our goals or objectives. Before this, there are some common bibliometric studies where so bibliometric studies can be done for the keywords or the subjects. For example, in this presentation, I said bibliometric study of fuzzy logic in Thailand. So I have used a keyword, fuzzy logic. We can do a bibliometric study for the countries as we are doing in this for the Thailand. I have also done bibliometric study for Taiwan and all the top 10 countries that are leading in the fuzzy logics. And nowadays, bibliometric study of journals is very, very common and important. But normally, journals do not agree to do the bibliometric analysis because sometimes the results do not match with the interest of the editor-in-chief or the associate editors, and they simply reject your paper. And if a journal, you are doing a bibliometric analysis, he rejects the publication, then you have no option to publish somewhere else. For example, I'm doing a bibliometric analysis of Thai Journal of Mathematics, and Thai Journal of Mathematics editor said, sorry, your work is not up to the mark, or I'm not agree with the results that you have discussed. So now that work is wasted. We cannot publish somewhere else because that paper is not of the interest of some other authors or the audience. So in these journals, there are some tricky parts and you have to be more focused on those ones. And the last one is institutions and authors. For the institutions, bibliometric studies can be done to highlight their progress, their growth, where they are aligned, how they are aligned with the sustainable development goals. When we normally, I ask to my colleagues, whenever they are going to present, they mention my work is more aligned towards sustainable goal development and my goal is to solve these sustainable development goals. But when I ask them, can you show me from your work where you have applied your work and it can be seen in the form of applications? So when institutes needs a report to file their rankings in time higher education rankings or all the international rankings, so they need to find out those sustainable goal development, and then they put their values and ultimately they get some rankings. So for institutions, bibliometric study is very important. And yes, till now, only one paper is found on the author's bibliometric. So there is a lot of space and one can do on their famous authors. So how this bibliometric analysis works, we have to use databases, Web of Science or the Scopus or Google Scholars. We need for the graphical purposes, Wasware and Sitespace. Similarly, at the same time, for topical analysis, we can use bibliometrics and biblioshiny packages of R language. And yes, statistical and MX Excel, these are very common. And can be used simply. How it works? First, we have to define research objectives. We have to select databases and research terms. We have to conduct a literature review, data extractions, bibliometric analysis, interpretation, and so on. So metric analysis, I'm not going to discuss. For the was-where analysis, we have downloaded our data and we were going to plot that. So now here, let us choose co-citation analysis. And before that, once again, recall co-citation analysis means used to identify research clusters and intellectual structures in a field. The purpose of this co-citation is to analyze the intellectual structures. So here we go for the co-citations. Sources in this software, source means journal. So in place of full counting, we select fractional counting and then we move next. Here it will ask minimum number of citations of a source, means for single journals, how many citations are of importance. So let us reduce this number because here threshold was very low. So it depends upon the data. For example, if we are doing for the very famous journal that has millions of citations or more than 10,000 citations, then here number 10 means are the clusters that will be more than 1,000. So we have to increase this number maybe up to hundreds, maybe 200s. But in this case, here when we select 10 citations, so we get 74 clusters. So that is okay. We move forward. Here we have now our values. So in any data processing, the important part is the normalization, filtering. So how to filter this data? If I click next, then it will simply gives me the plot. But I have to filter this data before going to plot this. So I will select all the data and export this data. Let's call it here. After exporting this data, we will go to our source where we have downloaded it. I'll open this data. I will copy it and then we'll go to some Excel file. Here we will paste it. When we paste the data here, we can see that this data is arranged alphabetically. And for example, these terms are not linked with the journals because we are doing a bibliometric co-citation analysis of the journals, and these are not journals. So these are some errors or some miss values in this data. So now we can remove this from this data, for example, this. So I will uncheck this box. Similarly, this one and so on. Uh, One can think this can be done here simply before our going to that Excel file. But sometime when you have more than one journals and they at the same time journals use their abbreviations and they have more than one abbreviation. So we have to merge all that data and then we will collect those values and again upload here and then we will plot that. Otherwise, a one journal in a simple single graph that may appear 3 times, that may appear 5 times. And similarly, if we are not going to do these filtrations, these irrelevant values may appear and that graph is of useless or the interpretation that we want to do is not up to the mark. So here we have selected all those values that was found irrelevant in this Excel file. For example, this one and this one. So after doing all this filtration, we will click finish and we will publish it. So here we have a graph of co-citation analysis of the journals, and this work was published by Thai authors. So here we can see that fuzzy sets and systems and information and control. These lines are the links. These lines are the links. This link shows that how strongly these journals are linked together. So in co-citation, our objective was to find out the intellectual connections between the documents. So the intellectual connections of the documents published by Thai authors in fuzzy sets and systems and information and control was of very high. So it means that if someone has published in fuzzy sets and systems, and then maybe its subsequent work was published in information and control. So in this way, it will help us. Similarly, we have many other nodes here, and it shows us like this one. So these connections. From here, we can change many options. What is the author's interest? Your interest is you want to discuss the citations or you want to discuss the links. So it is preferable to use the citations because links sometimes are not up to the mark or maybe have some errors. So most commonly we use here citations. From here we can use scale size, we can change it, and we can increase the number of lines. When we increase here the number of lines, cluster becomes more dense. And when we reduce these lines, cluster becomes very easy to read, and this one, like this. Only nodes, 100 relations, 100 links between these journals. Now here 100 links, what are the meanings of 100 links? 100 links means the documents published between, for example, in these two journals has 100 common keywords. Links means keywords here. So the document that was published in fuzzy sets and systems, at the same time, the document that was published in information and control, in both the documents, there were at least 100 common keywords used. So this is a very quick and a simple overview for just a co-citation analysis of the journals. Similarly, now we can do co-citation for the topics, co-occurrences, or bibliographic coupling. So this cluster is of importance. Yes, sometime when some authors take print of this cluster and then they put it in their paper, there are some missing nodes. For example, when I copy this cluster from here, so maybe this cluster or these clusters are unknown. They have no values. Then we have to manually add the names of the journals. How we can add those? We will copy this image. We will go to the paint and then we edit the name of this cluster. For example, now here we can see that this cluster, before this, it has no name. When I click here, we can see that this is the journal proceedings of the IEEE. So we will go to the paint and we will write proceedings of the IEEE for this node. So this is a short overview for this. And yes, I have done a complete analysis for the fuzzy contribution of Thai authors, but just for the large number of audience, I have just changed my topic and we have discussed this. So if you have any quick question, you can ask me because other speakers are waiting. A very quick question. Yeah, sure.
First, when you start this topic, there was no data on the net when you start linguistics. At the very start, because
Yes.
but and you said that till now you have 10 documents over there related to your topic. Until that, nobody is doing working in stream.
And two?
Till yet, nobody is doing work in your field that you are doing.
Yeah, it's author's interest. They are not
So you are the
of
only
more
one
interest.
in this field.
Yeah. And if you go to the link hypersoft sets, I have published, I was the first author who published a book on hypersoft set theory. Okay, and then at that moment, I have in that book, I have mentioned a large number of directions. So author started working on the extensions, fuzzy hypersoft set, intentionistic hypersoft set, Curran hypersoft set. So when I explored and when I did a literature review, I found that all those topics are based on linguistics and there was no work on linguistics. So I decided to go back and they decided to move forward. That's why. Yes. Related to this was where, yes, doctor, please.
When we look at this presentation, it's like it's more of a history combined with review of literature. Now, my question is, how is this type of research going to help someone? Because it's like the results in this papers are not presented. So since the results in some of these literatures are not presented, so how is this going to help somebody who is just a new researcher in order to identify the gaps in this area so that he can build on those gaps?
Very good question, doctor. There are two answers for this. The first one is the first purpose or the use of this bibliometric study is same as we do our first chapter for paper writing or the thesis writing, that is a literature review, right? And when we are doing a literature review, what we do is, or what is the data that is a very limited number of papers. For example, now you are working on convex something optimization in machine learning, and you have to write, or some reviewers ask you to cite more relevant publications in your work. And what you do, you will simply go to the internet, you Google it, and then you will write, right? Is this the way? So there is another way. You simply go to the Scopus database, write your keywords, that will gives you the most relevant document that is linked with your work, that may be published a few hours before you are going to download that. So this is one. So it helps you to write more recent, more relevant research papers to your work, right? And yes, now coming to your second question, that was how this will help the new researchers to analyze this. Yes, when someone is a new researcher, for example, if I am a new researcher, I am doing a bibliometric analysis, and I don't know the name of symmetry. Symmetry is a journal, and there was an old name for that journal, Symmetry Baser. So if there is a new researcher and he is not aware with all the terminologies that are being used, so he may confuse. But yes, a new researcher, with the help of co-occurrences analysis, he can find out most prominent or in examples in which most relevant, most researchers are working nowadays. For example, now for me, I have, as there was a question that no one has worked in this. Yes, because there was a huge gap in the foundation. So I decided to work this. Yes, now I have made that foundation. When I do a bibliometric analysis for the hypersoft set theory, I found another research gap that till now no one has merged hypersoft set theory with deep learning analysis. So since deep learning analysis sometimes maybe need to consider those techniques that are unsupervised. So yes, there is a gap. The most common machine learning techniques that we mention in our paper are supervised machine learnings. But unsupervised machine learnings are linked with data assimilation. For example, a weather data that is changing every second. So in my future work, I can combine data assimilation with hypersoft set theory. right? So in both the way, in literature and in future direction, it helps this. Any other question? Yes, sure.
Thank you, Doctor, for your presentation. Are there any mathematical models you use in this analysis, or all the analysis are done by the computer?
All right. Bibliometric is a statistical and mathematical analysis. Mathematical simply means counting. H index, I10 index, simply the counting of our individual research papers. This is a simple mathematics. And then we call it a statistical analysis. This was where software used some statistical relations here. So for this normalization, which method we are going to use? No normalization, association strengths, fractionalizations are like this. All these are back-end statistical algorithms that are used in this analysis. But unfortunately, those are built in, right? We are not doing manually right now. I'm sitting here and calculating the mean, median, or like this.
So although being used by the software,
Sorry?
the work is being done by the software,
Yes, being done by software.
you don't have any mathematical model that we use.
Yes, we have no mathematical model. Thank you so much. Yes, any other? No? And thank you so much for listening.
Okay,
Yes,
thank
this
you.
one.
Thank you.
Click.
Sorry for the inconvenience.
Yeah, it's okay.
So
it's
these
okay.
are my dissertation committee. So I'm trying to present my thesis within 30 minutes. So I think you will give me a constructive comment on that. These are the objectives of my dissertation. So the first one is to propose new inertial and alternative inertial iterative algorithms for solving split feasibility problems and its generalizations. Like a split feasibility problem with multiple output sets, multiple set split feasibility problem, and so on. The second is to propose inertial algorithms for solving fixed point problems. As we know, fixed point problems are very general problems. From that, we can have many problems. The other is to propose inertial algorithms for solving combinations of fixed point problem and a split feasibility problem, and to analyze the convergence property of the proposed algorithms, and finally to verify the proposed algorithms using numerical experiments and apply them to solve image restoration problems. So these are the problems considered in general. We have fixed point problem, split feasibility problem, and we have generalizations of split feasibility problem and combinations of these problems. So I have tried to present in three main parts. The first one is introduction. Second one is main result and numerical experiment. For sake of saving time, I will not talk about the preliminary part where we have many definitions, lemmas, and so on. And finally, I will give some summary or conclusions. So the first point I would like to discuss is about fixed point problem. As you know, many problems appear in many fields like engineering, chemistry, biology, physics, mathematics. We can reduce them to a fixed point problem so that we can use iterative algorithms to solve those problems. So a fixed point problem is simply a formula or a rule which takes X star to itself, where the operator T is a mapping from C non-empty cross convex set to itself. We have many mappings like strictly pseudo-contractive, Calvin and expansive, and so on. Demi-contractive, and so on. So we have many iterative algorithms which we can solve. For example, the most popular one is the MAN algorithm, but it has its own limitation because it only gives us weak convergence, and the convergence rate is very slow. due to that many authors or many researchers, they try to incorporate inertial extrapolation methods so that they improve the rate of convergence, so that they make faster than the Mann algorithm. But for example, if you take the algorithm which is given by equation 1.4, it has its own limitation because it requires to calculate alpha n, the operator, the parameter alpha n at each step, so that it will negatively affect the rate of convergence of the method. So this is that, for example, Bott and Silnek, they develop an algorithm by reducing the strong condition given by Mange to weak convergence. But they use only one inertial extrapolation method, and later Dong and others, they introduced double inertial method, which is shown by equation 1.5, and they give very simple conditions D1 and D2. The other problem we consider is split feasibility problem, where it is a problem of finding a point X star which belongs to the non-empty closed convex C, which is a subset of the Hilbert, real Hilbert space H1, such that its image under the linear boundary operator T belongs to another set Q, which is a closed non-empty closed convex subset of H2. This is how we depict the definition, where here X belongs to C intersection the inverse of A at Q. This is problem, split feasibility problem is very important problem because it can be served as a unified model for many problems, because we can transfer them to convex minimization problem, fixed problem, variational inequality problem, as shown here in this slide. There is a popular algorithm apart from that of the first author which introduced the split feasibility problem, that is Sensor. We have this popular algorithm because in the case of Sensor, the algorithm requires to solve the inverse of the operator. And we know that finding the inverse of an operator is not an easy task. Sometimes we may not have the inverse of that operator. So due to that, it doesn't become popular. But later, Byron introduced algorithm, which is shown here by equation 1.7. But it has its own limitation because, as you can see, the step size depends on the operator norm. And the other is they simply consider any closed convex subset as C and Q. So this is the limitation. To stress on the first point, that is the fixed step size, they use a fixed step size, one, which has its own limitation. The other is the step size, the tau n depends on the operator norm. And we know that finding an operator norm is not an easy task, especially when we consider the finite dimensional case. If the operator becomes, for example, a dense matrix, it's not easy to evaluate the operator norm. So it has its own limitations. So due to that, several authors, they introduce methods that solve the previous problem. Actually, in this case, for example, in this slide, you can see they only consider, instead of taking any closed convex subset, they consider half space, because in the case of closed convex, enclosed convex, the projection may not have a closed form. So it is a difficult problem, and it has an effect on the convergence rate. But still, they consider a fixed step size, which depends on the operator norm. And later, Yang, Yu, and others, they introduced another algorithm, which is self-adaptive, and they use a special closed convex sets, like we, as you can see, by equation 1.12 and 1.13. These are suitable for when the sublevel sets and Q are sigma strongly subdifferential functions on H1 and H2. So they come up with this type of closed and convex subsets, and they develop an algorithm 14. As you can see, the step size tau n here is a self-adaptive algorithm. So it solves the problems where we have fixed step size. The step size depends on operator norm, and the previous authors consider any closed convex set which have directly effect on the projection formula, because we cannot have closed form. And we are also working on the generalization of split feasibility problem. The first generalization is the multiple set split feasibility problem. As you can see, it is given by equation 1.16. So if you take, for example, t is equal to 1 and r is equal to 1, you get simply split feasibility problem. This is how we express the multiple set split feasibility with problem with multiple output sets. And we have also, this is a problem, the solution set is given by 1.17, as you can see. And to solve this problem, first we consider P of x in order to measure the distance of all of a point to all sets, which is given by equation 1.8. So using this square approximation, we can find an algorithm which will help us to solve the multiple set split feasibility problem. And a number of authors worked on this problem, like for example Suntai and others, Tardell and others, and Tan and others. So there are a lot of works on this area. The other generalization is a split feasibility problem with multiple output sets. So here it is given by equation 1.19. So if you consider, for example, S is equal to 1, this problem reduces to the original problem, that is the split feasibility problem. This is how we express grammatically, where we have three operators, A1, A2, A3. We have three output sets, Q1, Q2, and Q3. So this is simply the split feasibility problem with multiple output sets. So this is the algorithm developed by authors, which is given by 1.20. The authors that I have mentioned earlier, Simon and others. So they prove the importance of the iterative squares generated by algorithm 1.20. They also proved strong convergent result by introducing the viscosity type, as you can see, by f of xn in equation 1.21. So using viscosity type or half-point type, we can change a given result, which is weak convergence result, into convergence result. But these problems, as you can see, they have their own limitation, because as you can see on the second bullet of this slide, beta depends on the operator norm. So this is a limitation of this method. So later they come up with another technique apart from that of the least square approximation. They show that the split feasibility problem, the split feasibility problem with multiple output set is a special case of the generalized Fermat-Torricelli problem, which is minimizing of the function f of x subject to x element of C, where f of x is in the form of double summation. So by considering this problem, which is a result of the Fermat-Torricelli, the generalized Fermat-Torricelli problem, it is possible to obtain another algorithm which does not employ the least square approximation. So in general, we can say that in order to approximate a solution of the split feasibility problem, many algorithms first transform this problem into an equivalent unconstrained convex minimization problem, and obtaining a minimizing element using the least square method. So what they did is the rich and Trian, they used the Fermat-Torricelli problem and showed that the split feasibility problem with multiple output set can be considered as a special case of this problem. Moreover, they provide an approach for solving the split feasibility problem with multiple output set in Hilbert space. So they develop algorithms which help to get strong and convergence results. The other more general, which is combination of the multi-set split feasibility problem and that of split feasibility problem with multiple output set, is the multiple set split feasibility problem with multiple output set, which is given here by equation 1.23. This is also the problem that we apply in our thesis, in my thesis. So I have two results on fixed point problems, and I have four results on, three results on split feasibility problem in the generalization, and I have also another one problem on the more general problem, which is the split variational inclusion problem. This is a first result with that we we depend on this problem, and then we try to this is on split feasibility, the combination of split feasibility problem and fixed point problem for a dummy class of dummy contractive mappings. So what we did is, instead of split feasibility problem, we use the split feasibility problem with multiple output sets. So our algorithm is a little bit different. I will show you later. So we come up with a solution set. Our solution set is a fixed point, the set of fixed point of S, the mapping S, intersection the fixed point, the solution of the split split feasibility problem with multiple output sets. So it is since the problem is a combination of fixed point and split feasibility with multiple output set, our solution set will be the combination of these two, the intersection of these two, as it can be shown in equation 1.25. And the other more general class of mapping is the split inverse problem, which is introduced by Sensor and his associates, and it is given by equation 1.26 and 1.7. So here we have it is a problem of finding a point x star which belongs to capital X that solves the inverse problem 1, and such that y star is equal to the the operator A applied on X star, which belongs to Y, which solves IP2. So by varying the problems, the inverse problems, IP1, IP2, we can have many problems. Such, for example, we can have split variational inclusion problem, generalized split feasibility problem, and so on. This is a simple definition of the variational inclusion problem, which is given by 1.28. And one of the instance of the split inverse problem is the generalized split feasibility problem, which is given by Tian and Jiang, which is given by equation 1.29. Here we have Z belongs to C, such that the inner product of B of Z together with X minus Z is greater than or equal to 0 for all X element of C, and AZ is element of fixed point of set S. So this is one instance of the split inverse problem, and it's called generalized split feasibility problem. So, for example, there are many authors studied on this work. For example, studied the following problem, which is similar to that of the previous problem. So our next result is we are inspired by the works of Tan and Jiang, which so we introduced a relaxed, self-adaptive, alternating inertial algorithm for solving variational inequality problem with a multiple set split feasibility problem with a multiple output set constraint. This is actually it is not published yet, but it is accepted in a good journal. So this is a problem that we consider that we have X star belongs to gamma, where gamma is the solution of the multiple set split feasibility problem with multiple output set, such that the inner product, which is shown here, is greater or equal to 0. So this is a more general problem that we consider. And so if we consider S is equal to 1, so we get the problem is reduced to problem 1.31 here. And we have shown an example which shows we can get a solution for this type of problem. I will show you later. So this is the first work that we have, or we extended the works of Dong and others. They use double inertia for non-expansive mapping. So we, instead of non-expansive mapping, we work on the strictly case contractive mapping, and we have a lot of conditions here because for such kind of mapping, we have to introduce this type of conditions. So we get a weak convergence result. Also, I didn't show here, but also we, by using the viscosity algorithm type, we also change the weak convergence result into a strong convergence result. This is our first publication. The second publication is we have these are conditions for this algorithm on 2.2, and we got a fixed fixed point. The solution set converges weakly to a point of the fixed point set of S, where S is the mapping considered here. So we introduce three inertial parameters, and we believe that we mathematically we contribute here a lot here, because the technique which is developed by the other authors is not only for one or two inertial parameters, but when we increase the number of inertial parameters, the technique will be more complicated. So we try to accomplish this one for getting a weak convergence result here. So, and the result is more general result here, because by considering different cases, our algorithm reduced to many types of algorithms as shown here. This is a strong convergence result we have. We have double inertia and we have strong convergence result. And also by changing the mapping T, the non-exhaustive mapping by replacing by the operator, which is in red here, shown in red color, we can have a method, another method, which is which help us to solve image restoration problem. So we consider two standard images of butterfly and cameraman, and we evaluate. We just try to recover the original image by our method and by the forward-backward splitting method. And as we can see, our method recovers better than that of the forward-backward splitting method in terms of image ISNR and the similarity index. We can show that our method is a better method than the forward-backward splitting method. This is graphically that we compare the signal-to-noise ratio of our method with that of forward-backward splitting method, and we can see that our method performs better than that of the method. And the other method, as I have mentioned before, is the multiple sets split feasibility problem with multiple sets. So we have considered a number of conditions we have here listed here, where we consider the closed convex sets Ci and Jk are given here, but we try to change them into this equation 2.6, equation 2.7, so that it will be half space, which is a special closed convex subset. And we can mathematically show that our CIN is a larger set which includes Ci, and our QJKN also includes QJK. So this is where we consider the level sets strongly convex sets. So our method is the ball relaxation method. We use a ball instead of that and it's possible to show that this CIN and QJKN are a ball with certain radius and center. So it's possible to show mathematically. So this is our first another algorithm on generalization of split feasibility problem. So we have step one, as you can see, which is not elementary one. In step 2, we apply the inertial algorithm. In step 3, we use the special case of the Halpern type, which will help us to make our algorithm converges, the scale generated by our algorithm converges strongly to solution set. And this is another step 4. This one, the major step 2.13, where we have a double summation here that comes from that of the fairly generalized Fermat-Torricelli problem, and we have another summation outside. So this is a problem which solves the multiple set split feasibility problem with multiple output set. Our method is self-adaptive method, as you can see by 2.14. So we state the proposition here, proposition 2.6, which shows that the Pn is a solution to the multiple set split feasibility problem with multiple output sets, and then we prove strong convergence to the projection of the our solution set omega here. We have considered two conditions here. And this is a numerical experiment where we consider H, H1, H2, and H3, H4, and we consider C1, C2, C3, and C4. This C1, C2, C3, C4, where we consider here a finite dimensional space. In our example, our work is on infinite dimensional, but here we consider the finite dimensional case where we have C1, C2, C3, C4, which are closed convex subsets. Similarly, we consider also H1, Q11, Q21, Q23, Q31, Q41, and so on. And we consider the operators Q4, which are clearly bounded linear operators. We construct the bolus CIN and QJ1N, which is as shown before. And we consider the sublevel CI and QJK, which is QJ1, which is given here. So we also calculate the metric propagation onto these balls. We can easily calculate because these are special closed convex subsets. We randomly generate the coordinates of OI and CJ, and the parameters are also given here. And we consider the stopping criteria to be it is less than 10 raised minus 8. So these are the numerical results where we, by varying the dimensions S, N, M, and L, we calculate the number of iterations required to convert the required solution by restricting the stopping criteria, and we calculate also the CP time required to convert to the required solution and the error, which is given here. This is the figures given here. The other algorithm also similar, but this one is a combination of fixed point problem and that of multiple set split feasibility problem with multiple, which is generalization of that of the work produced by Barinde and Barinde. So this is, as you can see, combination of fixed point problem and that of, and the fixed point problem mapping is here is K-demo contracting mapping. So if you consider RL here, R lambda here, if S is K-demo contracting mapping and lambda belongs to 0, K1 minus K, so this R lambda becomes quasi-linear expansive mapping. So the algorithm is for a K-domain contracting mapping, but by utilizing this average mapping, we can reduce it to quasi non-expansive mapping. So you can apply the definition of quasi non-expansive mapping, the proof of this theorem. So we use a viscosity type here, so we get a strong convergence result. The theorem is stated here. Another algorithm is we apply here alternated inertial algorithm. We know inertial algorithms have some limitations because they lack the socket generated by algorithms which utilize inertial algorithms. They lack phasor monotonicity. So to recover the phasor monotonicity and Mu and Peng, they develop alternative inertial algorithms. So the inertia is only applied as odd terms. On the even terms, we have Tn, but in the case of the odd terms, we have inertial algorithm. So I applied alternative inertial algorithm to solve variational inequality problem, where the constraint is the multiple set split feasibility problem with multiple output set. So the first part we have where it helps us to solve the variational inequality, and later we have algorithms. We have algorithms which helps us to solve the multiple set split feasibility problem with multiple output sets. So this is another very important result in my understanding. So there are different conditions we consider. For our example, we consider the operator B here, which is given by nx plus q, where n is given here. D is an M by M diagonal matrix. E is an M by M matrix. F is an M by M skew symmetric matrix, whose diagonal entries are non-negative. So N becomes positive semi-definite, and Q is the vector which is a subset of Rm. It is clear that B is, from this definition, there is a result which shows that if these conditions are satisfied, then B is monotone and Lipschitz is continuous with constant L, which is given by the norm of N. So if this is the case, then clearly it is pseudo-monotone on and uniformly continuous. These are the conditions that we stated in our algorithm. So we state that the operator B is pseudo-monotone and uniformly continuous. So using the upper definitions, we can satisfy that B is pseudo-monotone and uniformly continuous, since it is monotone and Lipschitz is continuous. And this is by varying the number of the values of S, N, M, and L, we get different results. Where we have actually this is and also by varying different the stopping criteria, we have different cases. So our method performance is very good, as you can see. At this point, it is to be honest, I try to get results which helps me to compare the results, but I do not get a similar result. So I'm forced to just simply illustrate my method just by taking different cases. This is a second example. So where we have the special case, that is split feasibility problem with multiple output sets. So we consider set C, Q1, Q2, Q3, Q4. It's possible to show that they are, and set H is Rn as given here. So you can see that they are simply closed convex subsets, non-empty closed convex subsets. And we take different operators, A1, A2, S3, and F4. And then by using elementary calculations, we can show that the solution set or omega here can be given by this. And we can find the norm of x is always greater or equal to the square root of 734 over 10. And we can show finally that this, so the solution set is equal to this one if and only if t is 0.3. So the minimum norm solution of the split feasibility problem with multiple output set is given by t star, which is given here. So we consider the these examples, and we show that this is the exact. This is mathematically we can find the solution is this one, but numerically our algorithm does it convert to this solution or not to t star. So that's one of our tasks. One of our tasks. So we consider different toleration stopping criteria like 10 raised minus 5, 10 raised minus 7, 10 raised minus 9, 10 raised minus 11. In all cases, even though the number of iteration increases, from 8 to 11, 18, and 48, we can see that the solution set is close enough to the exact solution, which is shown here. And we also take different parameters, suitable parameters, which will help us converge. So the my conclusion, actually there is one result here, because maybe I'm afraid that I will not have much time, so I didn't include one result. I have a total of 6 results, so I only presented 5 results. So this is a conclusion. So we developed inertial algorithms for solving fixed point problems and relaxed self-adaptive inertial algorithms for solving fixed point and split feasibility problem, and we prove strong and weak convergence of the sequence generated by these algorithms. We also developed algorithms which solve the generalization of split feasibility problem, namely split feasibility problem with multiple output sets and multiple set split feasibility problem with multiple output sets. And we consider, instead of least square method, we apply we adopted the generalized Fermat-Torricelli problem and later we also develop algorithms which can solve fixed point problems and variation problems with split feasibility problems. In order to improve the convergence property of the proposed algorithms, we employ the relaxation method as well as the inertial and alternating inertial techniques. And we show applications of our proposed algorithms in solving image restoration problem. We also show that our main algorithm can be applied to solve different theoretical problems. Actually, I'm afraid this I didn't include here, but we can show that our algorithm can be applied to solve different problems, minimization problems, and so on. And finally, to illustrate the convergence of the proposed algorithms, we consider numerical examples. Thank you for your attention.
So, Dr. Jamilu, our invited guest, and it's our honor and to listen, Dr. Jamilu. May Dr. Jamilu proceed? Dr. Jamilu, do you listen?
Hello,
Yes, welcome, doctor.
can you hear me?
Yes,
Good
yes,
afternoon or good evening from Nigeria.
afternoon.
Good morning,
Okay,
doctor.
good morning. So, like we know, the talk today is going to be on the self-adaptive Part2 single operator algorithm for extreme learning machine in plant diseases. So, let's go into it. This work, we try to address the problem of finding a point in an Euclidean space such that for some operator at that point will be 0. Where this operator A here is a nonlinear operator. So we are all familiar with this kind of 0 problems, because we're trying to find the 0 of this operator. This problem is important, as we know, in many applications such as neural network, support vector machine, extreme learning machine. In general, this problem can be applied to a lot of machine learning problems, which we see some of them from the neural network, support vector machine, extreme learning machine, which are widely used in classification, regression, clustering, and feature learning. So among all these applications, one of the interested in that is attracting attention of researchers nowadays is the extreme learning machine, which was introduced by Huang in 2006. So the idea of extreme learning machine is a single layer feed neural network, unlike the classical neural network that we know, where you have multiple hidden layers in order to do classification or regression. This one is easy in such that it has only one hidden layer, and is strong in terms of its rapid training and generalization. And how do we compute now this extreme learning machine? So instead of the classical, for instance, the back propagation, in trying to get the output weight there, we try to calculate the updates, then we use back propagation to get the particular values of the output weight. In back propagation, differentiations will be involved because you have to compute the gradients, but in of the biases and the weights. But in this case, we are randomly initializing hidden weights and biases, reducing the training everything to just solving this linear system of equation, which is HZ equals to Y, where H is in this is the hidden layer output matrix, and Z is the output matrix that we are interested in. So in the standard setting, you see when you want to compute, when you want to solve this equation 2, the issue here that will arise is you need the inverse of this H. So as we know, inverse of a matrix, especially in the case of applications where you are dealing with high dimensional data set, normally computing this inverse might be very expensive, and in some cases, the inverse might not even exist. So there is a standard approach by using an approximation or pseudo inverse of that H, which is called the Moore-Perot pseudo inverse. For those interested, they can check out how to compute that inverse. So the issue with the computation of inverse, like we said, in general, is computationally expensive, and sometimes it can be even unstable in a situation where you're dealing with ill-conditioned problem. So how do we mitigate this? One of the things that were introduced is the regularization of this equation 2. You can see now here, this is the regularized version of it, which was derived from the minimization of the least square, as we know. But here, since we are interested in the nonlinear equations, our problem will come in this form with tau as the regularization parameter. So now, this is to use to compute the Z. So you can see we are familiar with this kind of regularized equations, which we can use our, so the question here is what will happen if we use our fixed point algorithm to solve this kind of problem? Is it going to be easier than using directly the Moore-Perot pseudo inverse? So classical methods that you can use to solve these problems, as we know, we can use the first order method like gradient descent, and the second order method like Newton type methods. But the issue with these methods, especially the gradient descent, is very simple. As we know, it has one evaluation, function evaluation, and the gradient and everything. But the issue is in computing the learning rate or the step size, sometimes it will be difficult to guess the actual good step size. Then you lead to slow convergence. And in the case of the Newton type schemes, we know that one, to use it, it requires the computation of the Jacobians, which here we are reducing, which might be very expensive. So in this work, we try to introduce a derivative-free scheme, which we can incorporate with this ELM to compute the output weight here. And to test the problem here, to validate our work, we are going to use a plant village tomato leaf diseases. This data set comprises of over 17,000 images across 10 classes of diseases. So we want to use this one to see whether our algorithm is going to be able to classify better than the actual ELM. Can we have a modified version? So this is the algorithm we have. As you can see, this algorithm is simple. We call it Part2 in the sense that this algorithm in the computation of the gradient, now just like the case of the conjugate gradient, it involves the memory of the previous gradient, which makes it improved. So this is how the algorithm is. You select initial points, you select a point here, and this sequence such that this is satisfied, And the update size for the learning rate here, delta n, is given by this. So it's self-adaptive. So you can see the issue now, for instance, in the case of gradient method, this one is a self-adaptive step size, and the update will be given by this. So one of the important lemmas we started with is this one, in order to get establish the boundedness and consequently the convergence. So suppose we have this operator where the set of the zeros are empty, then we can have a constant such that, so this equation 4 is a kind of a condition. Somebody, the inner product of a at y minus x star is greater than equal to some number delta and norm of a at y square. So we can have this result. So somebody may ask whether this is a strong assumption. If you look at it closely, this assumption is really relatively related to the strong inverse assumption of the monotonicity of A. But at the same time, this one is a little bit bigger than those ones, because we can give example. We make a remark here that these classes, they include the strongly monotone operators and the inverse strongly monotone. And also, if you check the lecture note, Yuri Nestrov also mentioned that the gradient of any convex and L-smooth function also satisfy that our condition. Where in our own case here, since we are taking the operator now to be this, so it's inversely strongly monotone. This operator is inversely strongly, so it will satisfy that condition. With the delta here can be given by this condition. So the following lemma also is a very known lemma. We know this one. We use it to establish the convergence. Just bring it here for inclusion. And this is the main theorem. We said that suppose we have this operator, it's a mapping that satisfies for, and we have a sequence generated by the proposed algorithm such that beta is choosing. For some of us that are working in this area, I'm sure we are familiar with this condition 5. It's not a strong condition. We can have many choices of beta and in such a way that we can have this is finite. Then for all points in the zeros, this sequence converges to a real number, which is the convergence we got it. So now I want to briefly discuss the pre-processing. Now, remember our application here, we are trying to detect leaf diseases and also classify them, particularly the tomato leaf diseases, which we said we have 10 different classes. One is a healthy one, and the second ones are, this is an example of the classes here. And this one is a tomato leaf with leaf mold disease. This one is lead blight disease and tigers. These are the kind of diseases. This just to give an instance here. I brought 6 different diseases, and we can have the healthy one. Like if you look at in this, this is and a healthy one. So what we do here now, how do you identify, then classify? For you to identify, you have to extract features. Why some of the diseases are easier to detect using leaves is because, you know, you can easily detect, even with your eye, that this leaf is not really healthy, and this is the healthy one. So that means that particular plant has some particular diseases. So to do this process, the process has to involve a lot of pre-processing. First of all, we try to pre-process with Coulomb filter. The filter is used in order to be able to get some more information. You can see here, for instance, this is the original leaf with some disease. Then after it undergoes certain filterization, we'll only change it to grayscale, where we can be able to demarcate, for instance, the shape, the size of the, because you cannot compare a unhealthy leaf and the healthy one. You know, the shape is different, the texture, whatever is what we are going to extract from those leaves, and we train the system in order to. So first of all, for the feature extraction, we are going to extract about 4 features. we will check the shape. In terms of the shape, we will look at the area. You know, those that have, if you look at the pictures here, from here, you can see from the area, those with the diseases might not be the same area with the ones without the disease. So we'll check the area, which I give the distribution, how we get this is the formula, we get the area. It's just the total number of the pieces within the leaf region. And also we check the ferrite diameter. So now with this binary image here, grayscale image binary that only have where the black and white, we can be able to see clearly where the area is and the perimeter here. This is just an illustration. And one good threatening thing about this one, if you look at this figure here, you can see here we have white. This one is telling you this leaf is taken from the one that is not healthy, because a healthy leaf will have the total black here. This also some of the things that we can be able to extract the features. Then we check also the color features. We have to extract how, you know, there, like for instance, yellow blight, you know, the leaves gets to get yellow than the normal healthy ones that are green. So we check the concentration of the RGB colors here, and we pick, this is the, for instance, in this leaf, and this is the RGB histogram in terms of compositions of the red, blue, and green channels that we have. And likewise, the HCB for the concurrence matrix here to get the relationship in terms of the color values here. Also, we extract those features. And then, and lastly, we extract the features here where we compute the contrast, correlation, energy, homogeneity in order to compare a trend between the malignant and the healthy leaves. So for the data set, like I told you, it has 9 distinct classes of plant diseases with 1 healthy. And look at the total here, the 19 here, the 9 here, about 17,329 images, diseased leaves, and 1,586. So you can see the class is highly imbalanced. In other words, we have a lot of the ones with the disease and few ones without the disease, which is also another issue in terms of classification, because this is a situation where the data set is not balanced, because you can have a lot of disease while this one. So if you are training the algorithm, chances of it taking the one that is not healthy and say is healthy is high, because they have a large number of them, which will address that one. One of the feature work is how to address this kind of imbalance situation. So as the machine learning tradition, normally the data will be divided into 2, which one for training and one for testing. In the case of this one, we divide it by 80 to 20%. So we keep the 80 for testing and 20% for training here. So this is, and we were able to extract those features. I told you we used 3 features: the shape, the text, the texture, and the color. So we were able to extract up to 67 unique features, which we trained to the model in order to identify. And we check the performance using different metrics, including accuracy, precision, F1, recall, and mean square error. So the regularization parameter, remember in our main formulation tau here, we are taking 10 raised power of 3 for the simulation. And we label the proposed algorithm 1 to be perturbed, as the name implies. And also we test with the non-perturbed one. Let's remove the perturbation and see what happens. And with Auslander's gradient descent method, which was proposed in this article, and also recently the inertial algorithm proposed by Vin in so, and all our experiment here, we stopped the algorithm after 3,000 iteration, and all the codes were implemented in MATLAB. So you can see the result here. We vary the number of hidden nodes. And theoretically, we know the more you increase the number of hidden nodes, the more you have more accuracy. We can see from the result here in the first one, we have 200 hidden nodes. The part 2 algorithm here, we have about 87.8 for test training accuracy and testing accuracy. So you can see these are very close. And the F1 precision recall and the RSM training time is 1.79 compared to the other ones. Here, in this case, you see when the fewer hidden nodes you can see here now, it seems that the gradient descent method performs, has high accuracy. But what does that tell you? That it's good with a fewer number of hidden nodes. So as we increase the number of hidden nodes, we can see we get more good result in the proposed algorithm here than the compared ones. That means this one, our algorithm is more stable in terms of the number of hidden nodes. And the more hidden nodes you increase, the more better of getting better accuracy here. Likewise, you can check if we add the hidden nodes to 600, still the algorithm consistently keeps improving while other ones are degrading. Because for instance, like the GD here is getting good, but when you add the hidden nodes, it's degrading, not really too much, but it's not really doing well. So in all the work, you can see that the proposed Part2 algorithm performs up to 95 point something accuracy here in terms of the accuracy and the time. Training time, relatively, they are competitive within all of them, but still, if you look at it, the proposed algorithm performs better. And to see the training accuracy, more accurately here, we try to plot the bar chart of the training accuracy for various hidden nodes here. You can see the legend. This is when it's 200, 400, 600 for each of the algorithm. And this is for the testing accuracy. And this is the confusion matrix. Confusion matrix here in such a way that you can know by class here, we try to represent for each of the class how well the algorithm is able to classify those classes. For instance, one here is representing the first class of the disease, the second one short like this, and the last one here, you can see the 10 is representing the healthy ones. And the percentage on the blue here is telling you the percentage of the ones got it right and the percentage of the ones that were not got it right. We can see that we have about 99.98.4 to identify the healthy one, which is very good. And you can see in all the classifications, they are all above 90. Only in the second class, we have a little issue of the classified one, only classified up to 84.0, which I'm sure it has to do with that highly unbalanced nature of the data we are using. And this is for the training and likewise for the testing accuracy for the Part2 proposed algorithm. And if you look at the non-Part2 here, you can see that there is a little bit difference with the other one, meaning the other one is improving. And if you can check here now, those values at the diagonals are the number of the element for each class that were able to classify correctly. The same thing with the testing for the non-Part2. And likewise for the GD algorithm here, you can see that, and then we try to plot the convergence to see, does it really converge? And this is the convergence plot for the residual. The residual norm is, we take the norm of the operator at the point and see. You can see, so we have convergence in this sense after like the 300 acceleration. And likewise, we plot the root mean square error for here we fix the nodes only to show the last 1,000 hidden nodes. So, and we can see in all the work here from the simulation, it shows that we have high improvement in terms of the classification when we use a derivative-free algorithm that we require to just compute a simple linear equation that dealing with, for instance, the back propagation, where you have to take a lot of differentiation. Okay, thank you for your attention.
Okay, thank you very much, Mr. Chairman, and thank you everyone in the lab. I really miss the lab, so it's been a while. The talk today is about on the noising. The title is on the noising color imaging, corrupted with salt and pepper noise via two-phase approach. So I'll go as fast as possible. So we have the following bullet point as outlined. So let's begin with the overview. So what are we going to do in this talk is basically structured or represented in this graph. So imagine you have an image, which is an original image, which is represented by this. So the first thing that you need to do in this kind of experimental setting is to insert the noise. So the kind of noise that we are talking about here is a noise which we call the salt and pepper noise. So in this case, an example of this, in this setting, we have a 70% of noise inserted to the original image. So this becomes a corrupted image that needs to be fixed. So now the question is, how can that be done? So the two-phase approach involves two stages. In the first stage, as you can see in this big rectangle, we have an adaptive weighted filter, bin filter. I will explain what that means. And then this actually is kind of like a filter that will try to identify those noisy pixels. And then after that, you will use a method called a variational approach or variational construction of an objective function that we will eventually use a method called MPPCG to solve. So this algorithm is an approach or an algorithm that will work over those noisy signals or noisy points or noisy pixels to recover them. So at the end of the day, the final output is going to be a recovered image, which in this case, as I represented here, which was carried out or done by MPPCG. So let's go one after the other, particularly the noising stage, and see what is going to be in that stage. So at the beginning, if we say we have a salt and pepper noise image, we are trying to say that, for example, an image with salt noise is an image that looks like this. So as you can see, since we all know image is just a bunch of pixels, so you can imagine some of these pixels were basically turned to 255. So this makes them a salty. So as the name mentioned, salt. So you see like kind of like a salt-like dotted points in the image. However, in the case of pepper, it's going to be kind of like a black dots that is inside this kind of image. So the salt and pepper is kind of like a combination of these two, having the salt noise and the pepper noise combined together makes an image which is called a salt and noise. So this kind of noise or impulse noise actually occur due to many things in real settings. So it does occur due to the transmission. For example, the image need to be transmitted from one device to the other, or maybe due to some environmental factors, maybe, for example, the weather and many other factors that could potentially lead to this kind of degradation of the image. So what are the techniques that can be used in order to do this? So there are many popular approaches actually that can be adopted to do it. So one of the most popular one is called adaptive medium filter approach. So all of these approaches, basically, their main goal is actually to reduce the noise while at the same time trying to preserve or reduce or maintain the fine details of those images. So imagine, for example, we have a corrupted image, Y, which consists of many pixel values, say yi, j, and we have an initial window, say z. And this z star or the hash here that we have, call it a maximum window size. So the adaptive medium filter is an approach that makes use of these two stages. So at the first stage, it involves what we call adaptive window size. So what that means is, first, we extract a sub-image. So we have the image, which is an image which is basically noisy. So we kind of like create a portion of sub-image of that with a given particular size, let's say z by z. And then we do some evaluation over that portion or that sub-image. So first we find the mean obviously, median obviously. So once we have the median, we also need to compute the minimum and the maximum of those pixels within that short window. So the final stage in this first step is checking a condition. So the condition is going to be, we are trying to find or identify if that particular median is strictly between the minimum and the maximum. So if that's the case, then the median is nothing but a non-noisy image. So it's a noiseless image, it's noiseless pixel. However, if it turns out that and so the process will continue. We'll move to the next step. However, if we were not able to do obtain this kind of setting, then that particular window that we started with is going to be incremented. So you can think of it as just a grid of points, it's a matrix, and the kernel will be kind of like going over all those grids of points or grids of pixel values. So the last stage is the detection or replacement. So this is kind of like once we realize what is a noisy pixel, then the question is how can we be able to either replace it or remove it or do something about it. So once it is identified, then it's going to be replaced by the medium. So you can think of it as just like having a grid and then you have a filter that goes over it and then do it as follows. Can you hear me? Hello?
We can hear you.
Okay, so this is basically the steps, and then the last point is just to repeat the process. So you can think of it, you have the many pixels, so you repeat the process until you are able to identify all those noisy pixels and replace them by simply the medium. So this is one of the popular approach, which is called adaptive medium filter. But it turns out that this idea or this approach of adaptive medium filter, it has some shortcomings, and one of the drawbacks of it is that it might end up missing the features, some of the important features of the image. Since you already have an image which is noisy, and at the same time, some of the fine details that are important to that image might be lost due to this replacement. So another idea that people try to come up with, I believe it was introduced in 2014, was called adaptive weighted mean filter. So here they are dealing with adaptive weights. So it kind of like introduced some notion of weights in trying to identify or in trying to do this kind of replacement that I mentioned before. And the method also have the same stages. So it has the adaptive weighted window state and then the noisy pixel detection and replacement stage. So in the adaptive window stage, it has almost the same procedure as the one mentioned in the previous slide, but it includes the computation of a weights. So the weight is simply defined in this equation number 1. So as you can see here, is just basically going to be either 1 or 0, depending on whether a noisy pixel is identified or not. And once that weight is obtained, we are just going to compute the mean by using this equation number 2. So the remaining stages are also going to be the same as the previous one of adaptive mean filter. So the final stage is basically trying to do the checking and the replacement of those pixels. And here, instead of doing replacement by the mean, by the median, we are going to do it by the weighted mean, which we define or obtain in this equation number 2. So these are some of the popular approaches to the best of my knowledge about this concept of filtering for this kind of noise. And then it turns out there are other ideas that were introduced, which tries to do it slightly differently. So one of these ideas is called a variational method. So in variational method, the idea is to, instead of doing filtering approach that it stated previously, the idea is to construct an objective function with kind of like a edge-preserving functional, which is defined like this. So this approach is trying to say that these filter-based approaches might end up missing some of the edges of the image, because since you are doing final replacement, so you are trying to like change the position in some sense of the pixels, which will end up kind of like degrading the edges of the image. So the variational approach is an approach that tries to mitigate this kind of challenge. And for us to explain it a little bit, first we need to define some few concepts. So first we have a neighborhood, which is defined as a set that consists of the, imagine you have a pixel at a particular position, I and J. So the 4 neighborhoods of that image, of that pixel, all of them for a particular, for each particular pixel, we have basically 4 pixel values that are within the neighborhood of that index. So we say we have the set of all those kind of points are inside this set that we define here. And then suppose we also have the knowledge or understanding, or we have a set that we call the set of corrupted fixtures. So this is a set that consists of the indices of these corrupted pixels, values of the image. So where this Yij is basically the corrupted pixel value, which is not actually going to be equals to Y bar. So why this Y bar basically here is trying to indicate that, okay, this particular Y bar is maybe a recovered one or a one that is not noisy. So the formulation of this objective function also involves the following formulation in equation number 3. So this NC dash is kind of like trying to say the complement. So if you remove the noisy, the remaining set of indices is united by this NC dash. So the objective function is simply formulated as this equation number 3. So we have the sum of S1 and S2, where the S1 is basically trying to sum over the noiseless pixel values. So since we are trying to take away these noisy points, and then in the second setting here, we are trying to go over or sum over the noisy pixel values. So why this phi delta is called an edge preserving functional, that some of the examples of this include the Hoover loss objective function or formulation or model, which is defined as a piecewise function defined like this. Or we have what you call Charbonnier penalty function, which is simply defined in this way. So this is kind of like an approximation of N1 loss. So now let's go through a little bit about what we have done or proposed in this talk. So first we try to we are motivated by, of course, the weighted adaptive weighted approach in the setting of the filtering strategy, and then the variational approach, since the filtering is kind of like an approach that can help, that can assist us in trying to find those noisy values or noisy fixed values, while the variational approach is, although it is useful in its own right in trying to preserve the edges, but we can we be able to combine these two approaches to have a kind of like a 2 stages strategy, where in the first stage, we first detect and track the fixed values that are corrupted. And then in the second stage, we try to recover them by using the variational strategy. So this is what we try to do here. And then to solve that formulated objective function, we then introduce a CG-based iterative method to solve it. So the algorithm or the CG-based method is illustrated in the next slide, as you can see here. So here we have we simply call it MPP-CG, and it has the input as stated like this. So, and then we hope to have a solution donated by this X star. And in the first stage, we do the initialization. So first we compute the gradient, since it is a smooth objective model, so we can be able to find the gradient at the initialization, and then we set the steepest descent direction like this. And the next step is just a condition, where in the first line, we try to find a suitable step size using these wolf-like strategies. And then we compute the direction as stated in this equation number 7, while the beta here is simply formulated like this. So this, in the denominator, we simply have a maximum between this first term and this norm of G and norm of K minus 1. So the next stage is just the update of these iterates. And finally, we have the final proposal for the algorithm. So actually, the convergence is just established over the standard strategy or standard assumptions over G and the gradients. And we end up having this classic convergence of subsequence of this iterate generated by the algorithm. So there is nothing fancy in the convergence result at all. So let's go to the experimental segment. So in the experiment, we make some comparison. So first of all, we consider the edge preserving functional, particularly these two, but for the sake of presentation, and I try to make it as quick as possible. So I only consider the first one, which is called the Charbonnier penalty function, where this delta is a positive number as mentioned earlier. And we also consider images from multiple sources. So here we consider the images from roughly 3 sources, just to have a diverse set of images and to see how the performance of the method could be over those images. And we make some comparison over some existing approaches. So all of these approaches were actually introduced in order to solve a grayscale-based image processing problem. So we first try to extend them for them to be able to use in solving or in solving a color-based image setting. And then all of them make use of adaptive median filter, unlike the proposed one that we try to come up with. So this is the proposed one, which we simply call it MPPCG. And the specification of the method of the device upon which we implemented these algorithms is stated here. And the metrics we consider for the performance, we basically compare roughly 5 metrics. So the first 2 are signal to noise ratio. So this is well-known metric for trying to evaluate the performance of these image processing based tools or methods, which is measured in decibels. And then we also have structural similarity index measure, which is also a very well-known tool in order to do this kind of metric evaluations. And additionally, you consider iterations, number of iterations, since all of these are iterative methods. So we try to see what is the number of iterations recorded by these algorithms. And we also consider what we call relative error. So this is basically a metric that's tried to kind of like a ratio between the difference of the image, the original image, and the final image that was evaluated, divided by the norm of the original image, multiplied by 100. So this is kind of like a ratio. And we also consider the time it took all these methods to be able to find a reasonable result. So for the, I simply stated the performance of this method based on these last 3 metrics for this particular talk. The remaining is in the work. So we have the first plot here. So this is a plot that tries to show the performance of these methods using the well-known Nolan-Armour performance profile. So this is number of iterations. So basically, we make use of the Nolan-Armour performance profile. On the y-axis, we have the success rate. So a method with a curve that has a number which is much more closer to 1 will be the most efficient one. And the other metric that we consider, as mentioned earlier, is the relative error. So basically here as well, we have on the y-axis, we have the success rate. So, and then on the x-axis, we have the proportion or the performance ratio. The last one also, which is also based on time, as you can see here, we have the comparison over all these previous methods. And one thing that you can note from these plots is that the MPP-CG turns out to do pretty well than the remaining method. And in fact, one of the methods like this MSCG is actually a modified spectral gradient descent method that does not even use any form of license. And one amazing thing here is that it turns out to the proposed one, despite the fact that it uses the Wolf-Lion search, turns out to be a little bit faster than that one, which is quite surprising for me as well. So the final segment is the issue of the visualization. So we try to visualize what is the performance of this method visually. So we simply took one of the images that we considered, which is a melanoma image actually. So this is the original image. So we have the noisy version of it, which consists of 60% of noise. And this is the recovered by the MPPCG. And this is the recovered image by the NPRP4. And this is the one by MSCG, TPRP, and MTPRP. So this just to illustrate how these methods are, and then what are their performance. In conclusion, we first introduced two-phase denoising scheme by combining the adaptive weighted mean filter strategy and its preserving functional. in order to be able to restore or recover an image that is being damaged by salt and pepper noise. And then we also try to introduce an iterative scheme in order to solve the regularization model that was introduced. And then we also try to perform some experiment in order to see what is the performance of this scheme over the existing approaches. Thank you.
Thank you for the presentation. Any question?
Hello, Dr. Mahmoud.
Hello, Doctor.
Yeah, thank you so much. I just have two questions. The first one is with regard to the number of iteration that you reported for the recovery of the image there. So
Okay.
what did you use? What did you use as stopping criteria there to report the number of iteration?
So the number of iterations of all the algorithms, we make use of the type. You see, for example, in the algorithm, we say the norm of G should be less than or equals to an epsilon. So this is the condition that we set. This is one of the conditions. Actually, we use multiple conditions, not only this one. The other condition that we also use is the difference between the function value at the current gradient, at the current point, and the function value at the previous point. The norm of that multiplied by some tolerance multiple of the function value at the current point. So there are considerable number of stopping criteria in the implementation setting that we use, but the one that we basically use is this one. To be able
No, I
to
mean,
do
I mean for the image just, okay, for the image experiment.
Yes, it is for the image, because look, we have the algorithm that solve the model. But before that, before the computation or before the iterative scheme, as I mentioned, we have the filtering strategy. So the filtering strategy is the first stage. And then once those points were identified, so you can think of this algorithm as just not necessarily taken from any random starting point, but rather taken from these noisy points that were noisy fixes that were identified. So all of the algorithms that were introduced for this kind of problem were adopting this kind of strategy of initializing the algorithms using those points or noisy fixes that need to be recovered. So
Yeah,
the
I
iteration,
understand that
the number of
one.
iteration, the number of iteration is something that you can record. K equals to 1, 2, 3, up to the number of times the tolerance or the condition that you set to the algorithm to stop reaches.
No, if you understand my questions, Dr. Mahmoud, I'm not talking about in general. Like in your own
Okay.
experiment, did you use the tolerance epsilon, or did you use the difference of the iterate, or did you use what did you use in terminating? For example, the difference of the iterate to be less than 10 raised to the power minus 6, or is it the difference of the iterate with this? So I'm interested in
I
that.
understand. So you are talking about this epsilon. What is the value of epsilon you use, right? If I understand your question clearly.
Yeah.
For example,
So,
this epsilon.
yes,
the
two things
stopping-
are
the stop-
involved. The value of the epsilon, and also did you use the gradient or did you use the difference of the iterate?
Good. So the tolerance we use is 10 to the power minus 6. That's the tolerance.
Okay.
And then for the condition that need to be satisfied, we use the gradient. We also use the other one. So the one I reported here is the one with respect to the norm of the gradients only.
Okay, norm of the gradient rest. Okay, I understand now. So the other question that I have is you see at the very first slide when you were presenting it, you said that you started by introducing a noise which is in form of salt, and is it salt and pepper or what? Anything. So my concern here is that so if you are the one to introduce the noise, why do we need to introduce that noise to work it out? Why can't we
Good
just
question.
work with the original image?
Good, that's excellent question. So the idea here is we are trying to introduce a method or a strategy, right? So in order to be able to justify or verify what will be the performance of that method, we need to be able to first try to do some experiment. And the experiment here, normally, when it comes to this kind of image processing setting, you have to be able to say, okay, since the task and the purpose of this idea of this introduced strategy or in this introduced method is to recover image that is in some form damaged by salt and pepper noise, right? So the question is, how can you be able to justify the performance of the method that was introduced? Okay, so in order to do this justification, you need to be able to know, for example, the original image, and then since you want to test the performance of the method in its in its ability potentially to solve this kind of problem in general, then you need to know the kind of noise that you need to insert to the image, right? And then to do the evaluation to see the performance. It's kind of like, for example, you have an example that you introduce an iterative scheme, you have an example, and you also know the solution of that example, of that problem, right? But you want to test the performance of that algorithm in order to see whether it was able to reach the solution that you hope the algorithm should. So this is the idea. It's not, for example, as you might probably see in the real applications, where you have an inbuilt implementation and so on and so forth that just take any random image to do the recovery. This is specifically done purposely for the salt and pepper noise at the beginning. And for salt and pepper noise, already we know the kind of noise that is going to be attached to these kind of images.
Okay, thank you. So in the final stage, Dr. Mahmoud, what do you have to say? Because now that we have to know the original image, and then we know the noise integrated image, then wouldn't it better to consider the recovered image by the algorithm and then compare it with the original image pixel by means of mean square error, then using the tolerance based on the definition of norm of gradient?
Well, I don't understand your question. Mean squared error in what sense?
Okay.
If you're talking about if you're talking about mean squared error, that's in some sense what is this relative error is doing.
Yeah, so I'm kind of interested, like, what do you think about that approach? For example, if you have an original image and the main aim is to get to that original image, so
Yes.
for me, I would say the ideal way is to check whatever, iterate that you have, stop your algorithm, check the results of the image obtained there, compare it with the original image and see how far does it differ from the original image, and that will give you the closest approximation or closest estimation of the original image that you may think. But just using the gradient.
So your question is twofold. So your question is trying to say, why can't we try to at each iteration to know the performance of the method in trying to recover the image that we are trying
at
to
the final iteration
recover.
Just not
what we did basically with this relative error is exactly what you are talking about. So this relative error is the norm, actually is a previous norm of the original image minus the recovered image divided by the original image multiplied by 100. So this is in some sense is related to the room to mean square concept that we are talking about.
Okay, but why do we have to divide by the norm of the original image? And my concern is not just about the norm, right? It's about the pixels themselves. Like
so if you take the difference, it's basically that's what we are doing, the difference between the pixels, since it is an image. So you have pixels. This is the pixels of the original image. This is the pixel of the recovered image at whatever iteration you're talking about. So you take the difference, it's going to be a point-wise difference.
Okay, but if you divide with another number, then you are causing it to be what?
That's the relative error metric, right? So you divide it by the norm of the original image multiplied by 100. So this is kind of like a ratio.
Okay, okay. I see the measure you use. Thank you very much for the explanation. Okay.
Yeah,
good.
you're welcome, Doctor. Anytime.